So I'm in the process of finishing some big projects, and then I have a house project I'm working on, so I haven't made a lot of progress on some of the other stuff. But I came across an old project that I thought might be interesting to share. And this is the second holiday light animated display that I built. And I think this dates back to 1995, 1996, something like that. It is a 4-channel chaser light display. And just to explain, this is back in the days we didn't have addressable LEDs. We didn't even really have LED lights. So what we basically had, you could just buy normal strands of lights. So what I did was I took, see if I can draw this sideways. So you take a string of Christmas lights. So you have a series of half-watt bulbs, the small mini ones. And they're about 4 inches apart. So you have that. So you take this string, and this string is white. And then you get 3 more strings, one red, one green, and one blue. And you kind of lay them down in this manner. See if I can do this without totally messing up. Okay, so that's not red, green, blue. So it's like a LED strip where all the LEDs are you can only set one color, kind of. So then you essentially end up with a strip with close bulbs. And they go white, red, green, blue, white, red, green, blue. So essentially I had 4 strings all bundled together and hooked together with wire so the bulbs were the same. And this was about as sophisticated as you got back then. So that was conceptually what lights I had, and that was to go around the house. And then you need something to drive it. And what I wanted was 2 things. I wanted to do chaser lights and different fades and that sort of thing between the different colors. And the important part there was I wanted to do fades. And to do fades, you need to be able to do dimming. And somewhere I wrote a magazine article on this. I'll see if I can find it. If so, it will be in the description. It was published in Nuts and Volts, and I think I received $50 or $75 or something for it. So anyway, conceptually, that's what it is. The code to do this. So let's move over. Let me see if you can see that. Okay. So this is the hardware. We have a 9-volt AC power supply. It's very important that it's AC. We have over here, this is a little board called the Bot board. It was designed to be used for robotics, hence the name. Here in the middle, we have a Motorola 68HC11 processor. I think it's running, maybe I can see the chip. I think it runs at 8 megahertz. That appears to be correct. So, processor here, some support circuitry. And then over here we have the rest of the circuitry. And to make this work, to do dimming of incandescent lights, you need to do phase control. And what that means is, I have a big drawing in the article, but very simply, you have your voltage looks like this over time. So, and this is the plus peak, and this is the negative peak. So, there's no, at the time, the way you would dim this is you would use a device called a triac. And triacs are kind of weird. They turn on, you put a voltage across the gate and they turn on, and then they stay turned on until you hit a 0 point. So until you hit here, or here, or here. So basically dimming involves just figuring out where these points are in time and then waiting a specific amount of time. If you hit that point and you turn right away, on right away, then you get full brightness. And then if you wait all the way towards the end, right before it turns off and turn on here, you get very low brightness, and then everything in between. And the brightness is proportional to essentially the area under the curve. But to do that, you need to identify these points. So you need what's called a zero crossing detector. And that's implemented here. I don't actually have, I could dig out the schematic maybe, I don't know if I kept it. But conceptually what I have, so I have 12 volts coming in, AC, and then I have a little full wave bridge kind of hiding in there. So instead of looking like this, it looks like this. Well, there's a little diode drop. So pretty much like that. So, sorry, pulsating DC. So I need to find these parts. And basically what I do is I have a transistor. Let's see if I can figure this out. Okay, so I have an NPN transistor. And basically I'm driving, I have a resistor here, and I'm driving this from the pulsating DC. And then this is connected to the 68HC11 input. And I'm pretty sure I have a pull up here to 5 volts. Maybe I do, maybe I don't. Conceptually what happens is the pulsating DC, the transistor will turn on as soon as I get a high enough voltage here, and then it will turn off when the voltage drops low. So I essentially have a way of going from this to, I think the square wave looked like this. So, something like that. And then conceptually what the code does is the code looks for a falling interrupt. It looks for this drop here, triggers, and it knows experimentally. You can measure when this happens on one channel of your scope while looking at the pulsating DC on the other scope, or even the AC input. And you can tell how much earlier this is than the actual zero crossing. So you essentially find this point in time, wait a little, and then that gets you right to the middle part. And then you can use timer interrupts to drive the rest. So conceptually that's what's there. The simple zero crossing circuit. This is, I'm sure, 7805 power supply. 2 capacitors, 10 microfarads for the traditional 7805. And then lots of stuff. This is a little old, ugly 10 LED decade all hooked together. And they're hooked together and they're driven by code. I just checked and it's actually the counter code. So you can see by looking in that the processor is actually running and counting, which is important. In general, this is a really nice board. The processors were fairly cheap, the boards were cheap. You could buy all the components and create them pretty well. And this is the second project I did with them. They had one pretty annoying characteristic, and they didn't reset automatically. And there were some nice chips that were designed to do the reset, but unfortunately they were hard to find and they were about as expensive as the processor. So what most people did was build a little RC circuit, which, I don't know which one, but one of these capacitors here is a little circuit that's designed to hold reset low for a little bit of time until the processor kind of wakes up, and then it will start up correctly. But that doesn't actually really work that well in reality. Some it does, some it doesn't. So what that means is if you're going to use this in a real display, you can't turn the power off and on, because when you turn the power on, it may just sit there. And what that means in reality for my displays that did this is they need to have timekeeping in them. So the software, all this software here ended up being written in assembly. You need to learn, I just went and checked, and the 68HC11 reference manual I think was 282 pages. And at the time Motorola would send it to you for free, which was very nice of them. And you could go through, the code for this was all written in assembly. And then you could look at one of the pages that told you how long each assembly instruction took, how many cycles it took. And then you could figure out how long your loops took. And from that you could figure out how long to run your animation. So the animation I think would run for 3 hours. And then you had, after that, it would flip to another part of the code and just run timing code for the remainder 21 hours. And then it would start over again. So you turn it on, reset it, and then it would use that kind of as the time base all around. Which is a huge pain in the ass if you ever get power hits or resets or something like that, because it means your lights don't work, or they come on at the wrong time, or just all sorts of fun. So anyway, that's the bot board. It was a pretty cool board and pretty robust. I can show you, I have 2 bulbs here connected directly to sockets connected into the system here. I used to have 4 of these. I'm kind of surprised that I still have 2 of them 20 some years later. So we can see if I plug in. The nice thing about embedded electronics like these guys is they actually don't tend to break. Although this one needed a little bit of surgery. Okay, I need to reattach the power. Needed a little bit of surgery because of power. Okay. So let's see, we should start with one light. Okay, so the initial animation is really, really boring. So it's brought on one channel, which is probably white, and now we see it dimmed across to the other channel. And it's going to sit there for a while. Now it's going to dim. Unfortunately, it's dimming across to channel 3. Oh, I guess we could, if I'm really quick. There, now 3's working. And now we dim across to channel 4. And then we'll go back to 1. And I don't remember what the animation did. It speeds up, I think, and does some other fun things. But that's basically how it worked. And this ran, I think I ran this for about 10 years. So that's the, and I don't know if you can see this, let me turn off the lights. You can see here we have just a little heartbeat counter. So it's just counting, it looks like it's counting down in binary rather than counting up in binary. But, and if I remember, some of these don't work. I think the 2-digit there is actually broken. There you can see. So it's just doing some counting, and this was just so when it was sitting in the box I could see it. And I never did another design like this, so the little debugging thing just ended up sitting on there. So that's how it looks at the low voltage part. I might let me unplug it, and now we can dig into the high voltage part. And all of this ended up in a, so the big chain, the big cable ended up along the eaves of the house, and actually went both ways. And it was very carefully designed so that the spacing, the ordering was the same, even though it went 2 different directions. And then this was all in like a Rubbermaid box that was held up under the eaves. So, screwdriver, and we can dig in a little bit more. I have not opened this in 20 years, but I used different kinds of techniques. This was actually a pretty good technique. You build something that fits into an actual outlet box. All the high voltage is contained in there, and that's pretty nicely. So we have the input cord coming in, and then this little output which just powers the control. And as I take this apart, I'll note that the reason I had it sitting around was I have a whole bunch of boxes, plastic boxes, that hold all my Christmas lights and animation stuff. And this was taking up space in one of them, and I finally looked at it and said, okay, that was really cool when you built it. And it's never going to be used for anything in the future, simply because all the technology has moved far beyond this. And some LEDs you can dim with that, but if you're going to do dimmed LEDs, you really want addressables. They're just way less hassle. Should have grabbed my impact driver for this. Okay, what are we going to find? Oh, of course, I took out the one that was really the wrong one. Okay, I need to pull out the other one too. You're just going to have to bear with me. So the 68HC11 is really fairly comparable to a lot of the other 8-bit microcontrollers out there. It has a pretty small instruction set, and my recollection is that writing software and assembly was more than a little pain in the ass, simply because it's a small instruction set, and sometimes it's not all obvious how to do it. So, real reason that programming in C is a lot nicer. You learn one thing, and you don't have to learn the vagaries of a specific instruction set. And somebody else has to know it well enough to do the translation. Okay, so you probably noticed already we have a nice little ribbon cable here. Look back here, all but one of the pieces comes across. So what that means is we have 4 conductors, which is of no surprise at all. I remember this now. Okay, so there were different ways I built these. I built a few different designs, and this was one of the designs where I used kind of a daughter board. So I don't know how well you can see, but these here, these 4 things, are the solid state relays. So 1, 2, 3, 4, they probably, I don't know what the specs are. Yeah, I bet I can see. Okay, so what does that say? NAIS, 2 amps, 125 volts AC. 5 volt DC in, and then load. So minus, plus, input, and then load, of course, don't matter because you're doing AC. So 2 amps, and typically what you see is you can find nice small solid state relays. These are really interesting in that they're encapsulated in plastic. So little boards and then dipped in plastic. And then if you want to go above that, you end up with the kind of big rectangular square ones. We've got some really nice corroded solder here. And then, of course, we have big cables running from here, and those run actually up to the outlets. If you ever want to do this yourself, if you ever want to build this sort of thing, by far the best way I found of building these is to take the solid state relays and physically hot glue them to the back of the outlets. And then they're just all together, and then you can access them much, much easier. And you don't have this problem of doing all these wiring between here. So that's about all we have. That was state of the art, or at least state of the art for me in the late 1990s, and I hope you found it interesting. Thanks.